right, everyone, how we doing today? Doing good? How's the class going? Silence? It's okay? We're all tired, ready for the week to begin? Week 9, October 22, 2025. So, how was that exam? Exam 3. Is it on convolution? Yeah. You guys do your convolution? What was the hardest problem on that? Did everyone get it right? I don't know. I'm just guessing. Was it a good exam? It was okay? How was the assignment? You guys saw that little extension? We had that AWS hiccup that we had? Yeah, I was thinking about it. I was like, I'm just going to force it to be due on Monday. Be like, yeah, actually, just kidding. No. I couldn't even send an assignment announcement at all. So that's why I said, I'll make it due next week. But it was funny because I had lots more questions saying, for problem 1, it asked me that. I'm like, what? You're asking how to solve problem 1 on an extension day? I don't know. So it's making me concerned. How are you guys' MATLAB skills? Struggling, suffering? You guys know how to generate a figure, right? You know how I'm doing those figures, correct? All I'm doing is just figure 1, correct? Stem, and then, I don't know, N, and then Y, or something like that, correct? And then you generate your N is equal to, see how easy this is? I don't know. I'm just creating some random numbers. And then this right here is going to be my Y is equal to zeros, 1 of N, length of N. Boom. Is that easy? You know how to instantiate figures? You know how to title them? Is that good? Is that what we were seeing? Were they putting the word figure in their homework? Yeah. Because if they have their figures and they're putting their stems, that's fine. Because this right here is what matters the most. But if they're just doing this, well, this is fine. Well, it's going to run, but that's not what I'm expecting them. Actually, is it going to run? F9. Hello? Evaluate. It doesn't evaluate. So no, you need to put your figure, okay? Figure 1 or something, whatever. Okay? Were they doing that in their homework assignments? Figure 1, figure something? Oh, it's just one student? Okay. But yeah, this is what I want to see for everyone doing their assignments. You have a figure. You guys know how to do subplots, right? Easy subplot. 2 rows, 2 columns on position 1, stuff like this. Is that easy? Or if I wanted to do something funny, I don't know. I want to do a unit step. U0 is equal to, unit step, which at the way of 5, I'm just making up a random number, which is N is going to be greater than or equal to 5. Is that good? This is a Boolean algebra, right? If I were to do the following, F9 gives me Boolean algebra, true or false. Is that good? And if I did this, subplot 2 rows, 2 rows, 1 column on the second position, what's this going to look like? N, U, 5. Like stuff like that? This is just learning the little tricks of MATLAB. This is not going to it helps with creating some pretty crafty assignments so that you guys can professionalize and use this in your other classes. But this right here is if you're naturally going crazy with it takes years, or not years, just semesters, practice. Literally just practice MATLAB. It's fun. But all I'm expecting is, if you know the bare minimum, which is, I don't know, this 2, 4, stuff like that, right? And then you're doing your title, Title 1, right? And this right here is, hold up. Nope, we don't want that. We want this one after that. And copy paste, stuff like this. Title 2. Is that gonna run? What? Oh wait, maybe you have to do this. Yeah, MATLAB takes a while to play with. There you go. Does that make sense? Stuff like that. Make your code clean so that the grader can do her job and make sure assignments are graded on time. Have you guys gotten your grades back yet? For any of your assignments? For the second one? Handwritten or the computer assignment? Computer assignment, was that good?
Yes.
What about the computer assignment 1?
You have like 6 people who's not. I haven't finished grading them because, as I mentioned, for one student, they just turned.
Yeah, it's okay.
Yeah, and then.
No worries, no worries.
Yeah, we just stopped grading them.
Yep. Well,
Show
yeah.
you their code.
I'll see it. And then computer science 3, yeah, you'll be on top of grading that. Don't worry, take your time, okay? Because they just submitted that yesterday. Yeah, yesterday, right? So, was that good? Was that fun? Understood? Let's go over it a little bit. Computer assignments. CA3, or I'm just going to type on this one. Currently writing your 4th one. Stuff like that, right? Block diagrams, correct? Is that easy? You guys got to saw the cool sinusoid? You guys like how I literally gave you the answer in class? You just needed to figure out your signs? Is that a good help? Direct form 2 is easy too. Actually, funny enough, which one did I did? Transpose? Or no, I did the direct form 2 because that one was the tougher one. Then was this easy? Yeah? Guys copy pasted? That's all that matters, right? You guys understood this, right? The actual figure. What are they saying? Yeah? Why? Because of that, right? It's just the same system, right? It's the way you change those gains, okay? Like the gains could be like going like this, or it's like this, or some other thing, right? But the problem is still the same thing, right? With the same conditions, right? And if I do, the Kronecker delta, a delta function, you're going to get the same answer. Is that understood? So I'm not looking, so when I told the grader, we're not looking for like the actual, yeah, that's good to know the actual final figure, but it's how you get there. Is that understood with everybody? What's going on? Then everyone understands how to do this one, right? It's just a bunch of feed forward blocks going forward, right? Right? B a 0, B a 1, B a 2, right? Same thing, right? You're just doing feed forward blocks just going this way. Is that hard? Or easy? Or we want to make it a lot easier? Not that bad? You put a Kronecker delta into this. What do you see? You saw that little, it was like a little pulse, right? Is that what you guys saw? Yes, no, maybe? Let me show you. I already do the following. Let's copy paste this. So do I want to copy paste this? And let's go. Boom. CA3. So if I define an H, and if I were to do the following, this is 1. You guys did this right here, right? Copy paste them. 2, and then you just do some copy pastes. 3, then this is 4. Boom. And then I'll show you another trick. I'm gonna call this one H. I don't know, left. H0. This is gonna be my 0.4, right? And then H right is just going to equal. So let me show you what I'm trying to do. if I have the following numbers, I'm just gonna do the following. I'm just gonna write some random numbers. Minus. Let me see what I was trying to show you. If my H response, H of, I don't know, T, right? I'm just writing an H of T, correct? What is H of T? What is that?
Impulse response.
Impulse, right? So what is an impulse response?
Sudden response.
Yeah, literally just a... Yeah, so if you hit this table or something, or I'm gonna hit this camera, you see how it rings and then it settles? That's an impulse response. So if I keep doing this, you'll notice that like ringing, right? That's an impulse. It's gonna always do that. Well, minus the base kind of moving like that. Does that make sense what an impulse response is? So if I were to do the following, it's like this, right? Then that's your impulse. It's gonna do that forever. But funny enough, the impulse response you guys were given was just this. It was really simple. Have you noticed that they were all feed forward blocks? They were all just going forward. So if this was x of n, then I'm going to do the transposed direct form to 1, 2, b0, b1, b2, right? And they just all add up. Right? Do I have anything going backwards? No, because it's all going feed forward. Is that good? So you're going to see this, like if I were to draw that, right? Okay? Does that make sense with everybody? So what I'm trying to do is, funny enough, you won't see this until you get to grad school, is that you typically, our impulse responses are written like this, like a sinc function, where we have this middle DC term, right? Right? So this right here is like our top, or like our DC if you think about it. And then this right here is our left. And this right here, actually a different color. It's our right. So what I was trying to do, I'm trying to create a mirror, right? So if I had the following, like boom, 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 and then this right here is just this middle point, and then this, it mirrors like this, right? And this right here has how many points? Or actually, is it n or n or is it even or odd number of points? 1, 2, 3, 4, 5, 6, 7, right? It's odd number points, correct? So I'm gonna do a funny trick. This is just a trick. This is what I'm trying to show you, just in case you wanted to build your own filters, which maybe I'll make that a design project. Not right now, but it would be cool to design your own filters. So I'm just calling this one H left. This is our first, second, third, fourth part, right? And I want this one, right? So all I'm gonna do is just, I don't know, H left. You can do it as many ways. I want the, what do you call it? Every column, no. H left. I want to go -1. Does that work? See, this works. F9. No. There we go. Let's see if this works. No, it's not going to let me do it. Let's use a function. Flip, left, right. Is that good? And then I'm going to create my, hold up. Yeah, that's there. My full H is going to equal to H left, H0, and H right. Is that good with everybody? Hold up. Why did it do that? What is H left? 1/4. And then H right is 1/4, right? What did I mess up? Huh? Right? Oh. Right, GHT. Thank you. Is that good? Figure 2. Stem. I don't know. I'm just going to put H. Is that good? Is that what we're generating? Is that good? But I want this to start at 0, right? Because that's what our function is going to do, right? When we're doing convolution, right? If I were to do the following, let me see. And we all did the circ shift, correct? So if I wanted to do an x, right, it's going to be zeros of, I don't know, 1 to size, no, length of n, correct? And then if I wanted to do for I is equal to, let me see. If you noticed, for our actual convolution, this right here is your answer. You have H0, H1 down to H9 or however many points, correct? And you notice that your first point, right, your delta function, right, x is 0, delta, right? Your first point needs to be the actual first point right there. Or of, let me just show you, run this again. Boom, Control R. That first point needs to be 0. Is that good with everybody? So, was there anything sketchy about this homework? Yes, no, maybe? Fun? Man, we wish we could have had an actual discussion on the homework, right? It's okay. But then you guys got to actually do some filters, correct? Actually, better yet, your solution guide. That's why the picture doesn't matter for Joanna. Is if you wanted to do the following, let me show you. X is equal to zeros of that. Then that's your H. Okay, I'm gonna do something funny. Figure 3 subplot. What do you call it? Nah, I'm just gonna brute force this. Y is equal to con. I'm gonna take my X and my H, right? And my H is already solved for, right? I already punched that in. Then my X, I want to put an input, right? I'm just going to do, I'm doing no delays, by the way, okay? I didn't do a delay. I'm just using this raw formula. You'll have to do your delays on your homework, correct? So I'm going to do, let's see. If I want to have a delta function, X is going to equal, what do you call it? N when it's equal to 0. Is that good? Yeah, let's run this. Nope, not that one. Figure 2 or 34. Or stem n y. What happened here? X must be the same length as y. So n is 1 by 51. And y is 1 by 59. Then let's give it 59 then. Let's force this. 0 to 58, or length of y. Just doing that for my own purpose. Minus 1. There we go. Boom. Is that easy? So is that what you guys got for your first answer? And then for both the block diagrams themselves? So conv is just your LT spice, your check and answers, all right? And then funny enough, you guys you actually saw the filtering, right? You saw how this little sinusoid got filtered out, right? Did you guys actually simulate this whole circuit, like this X itself? Generate 8 plots, right? Plot the input and the output, right? You guys got to see that crazy signal? Was that fun? Right? X is equal to, let's see, cosine 0.05. I'm just going to call this one x2. Dot times pi dot times n, and plus sine 0.6 dot times pi dot times n. Then I'll just keep it like that. anyways, if I were to do the following too, exit 2. But I want to show you guys subplot 2, 1 of 1, stem n and x2, subplot 2, 1, 2. Look at that. You guys saw that cool stuff? Look at this ugly signal, right? So intuitively, what does this 0.05 mean to you? Omega or 2 pi f, right? Well, there's no 2 pi in there.
There's a pi already.
Yeah, there's already a pi there. So this is basically 2f. So that means your frequency would be about like 0.025, right? So it's a very low frequency, correct? So what I'm trying to say is this frequency, right, compared to this, can we agree that this is a much slower signal than this? So what we're basically replicating is noise. This right here, or not noise, it's just it just messes up your signal, correct? But now we gotta filter that out. Look at that, filtered out pretty good. So is that fun? This is just introductory to filter design. So in 480, you guys are gonna be designing this, all right? You guys can design your own filters. And then in 780, so that's our highest level signal processing, you'll be designing like some crazy like neural networking and using adaptive signal processing. So that's where, so these are already calculated. You'll be designing this like 2-3 years from now. Sounds cool? Any questions? No? So let's see, what do I have for your next assignment? So this is computer assignment 4. I'll be posting this later today. What's his name? Look at that. Same signal, okay? So you've already done this, okay? Draw a direct form 1 block diagram of this and determine the system's impulse response, okay? So and then, what do you call it? Zero state response, ZSR. Have you guys studied that, ZSR, yet? Yeah? Okay. So zero state response means there's no states. So that means, what are you looking at? The input, right? So what does that mean if I kick the box? Impulse, right? Just hitting the table or wiggling, I don't know. Just impulse, okay? Impulse response. So what does that mean? You're going to be solving for h of k, okay? Is that good? And then using a for loop, calculate it. Using a actually, let me see what's going on. Oh, why did it skip a number? Should be 2. Where did my numbers go? Let me see the original PDF. That's what I was trying to do. CA4. There you go, original PDF. Yeah, I have to erase my numbers like that. So I actually gave you a hint, and this is what I've been trying to do to make it easier for you guys. So you're setting your actual output at n is equal to 0. You're setting something up, okay? You see, show your work. H of n is equal to h of zeros, h of poles. Yeah, literally you're developing the system state response, okay? Or an impulse response, all right? And then what did I do here? Determine the values of R for which this system is stable. Remember the Schwarz inequality? So what happens when I make this system, like if R is equal to 0, or not 0, 0.99 to 1, 1.01, right? What happens with this? If it's bounded input, bounded output. Is that easy? Good? Then write a program to implement your direct form 1 block. You're just literally using the same stuff from the last homework, okay? Calculate the first 51 outputs, and then you're gonna see it start ringing, right? You saw that ringing, correct? So if you have like what do you call it? Yeah, you'll see this. This one's decaying. This one's constant. This one's just gonna ring a little bit. Actually, do you guys know where this equation comes from? Yes?
Which equation?
Or not equation, but where this function actually is modeling from. So it's actually a sinusoid. So I'll tell you that. That's the answer right there. This will be on an exam problem. Everyone always gets this one wrong. So that's why I made sure to put this on the actual assignment to say, hey, this is a sign. You'll have to reverse engineer this. Remember Euler's equation?
Oh, yes.
That's exactly how you solve it. And you'll realize it's just a sinusoid. So that means when you use r is equal to 1, what are you going to expect? Sinusoid. All right? That's your biggest tip for everyone here. Okay? And then 0 input response, okay? You guys know how to do that?
We learned it today.
Okay. Let me just show you a little bit. Page 1. Let's use the next page. So ZSR, right? So what did I mean by H of zeros and H of poles? Is this the first time you guys are hearing H of 0, H pole? No? Yes? So basically what I'm trying to talk about, this is basically your feed forward block. And this is your feed back. Anytime you have something going forward and not coming back, you know it's going to be, well, the answer is going to be a 0. It's a 0. It's not going to blow up. But if you have something feed back, you can always make it blow up. So you'll see these poles. You'll learn that in the next assignment, which is Laplace. You guys will be doing with Laplace transforms. So that'll be pretty fun. That's where the big cheese of this class is Laplace and Fourier, right? So for your ZSR, right? Let's just say I have some, I don't know. Let me just do something random. I'm just gonna draw some block diagram. B0, B1, right? Is that good? And that's all sums into some node, right? C of n. Is that good with everybody? So zero state response, right, is where everything inside here is 0, okay? But you're gonna kick the box, all right? So if I drew our little guy right here and he's gonna have his big boot, he's gonna kick the system, right? He's gonna throw a delta function. Is that good? So at time is equal to, or not time, n is equal to 0, right? What's the first thing that's coming out of that box? Actually, is this B0, right? But then I drew this one wrong. Let me show you. It's supposed to be a D in there. Does that make sense? Because there's delays. So now that delta function went away, now it's gone, right? So now that delta function is, now we're at n is equal to 1, right? And now that delta function's over here, right? N is equal to minus, or not minus 1. How do I say this? So the 1's right here, right? And now the 1's out. Got this B0, correct? Now the 1's right here, right? Is that good? B1 times that 1. So that means that n is equal to 1, or n is equal to 1. Our output's going to be B1, right? So what does that mean when we just put an impulse to this zeros?
Same response.
Yeah, you're going to get the impulse response, right? So what does that mean about if I were to tell you this is a company, right? Company A, right? Right? And I say, I'm going to design this, right? And I say, what's the impulse response? Well, yeah, H of n times x, or actually, I think I gave you guys the answer, but let's just say, is that how I want to show you? No, let me show you a different way, because there's a better way to show you this. What other letters did you guys use? Not H. What's the other one?
G.
Huh? G?
I would just say.
It's okay. I don't know.
I would use that.
No, you're not wrong there because you don't know what this is,
Yeah.
right? So that means what happens when our x, right, is equal to our delta. Anything convolved with a delta function gives you the anything back. Does that make sense?
Yeah.
So that means you've already built this. Congratulations, you're done. All right, is that easy? This is what's going to go into your next part, but let's not think about that first. We're going to actually kick this box separately, okay? So you have your h of zeros, all right? Is that good? Okay? So don't worry about this. This right here is how you solve for that. It's the easiest part. Don't fail this. This will be on the exam, okay? For either the differentials or your difference equation, okay? This is actually, I don't know, this is like a good 5-10 points just to get this right there. Is that good with everybody? Let's design our next part. So I'm gonna design our next part. It's this pink marker, okay? Company B, right? And then I have, I don't know, I'm just gonna do something funny. Plus, then there's that. And then I'll put the fingers going in there. Let's do this. A of 1, A of 2. This is a direct form 2 block. Transpose direct form 2 block. D plus another D. Right? So now you're going to design this one, okay? It's the first thing you got to do. Kick the box, right? So I'm going to put a 1 in there, correct? All right, now that 1 is going to go into here and into here, right? But now we're going to have to say, okay, what's y at, or what's the output y at n is equal to 0? Just 1, right? Because you kicked the box, all right? But now this one's going to start going back in there, and now this is where you're going to have to start finding your, what do you call it, your auxiliary equations, all right? So if I were to show you the following, this is going to help you do your homework. This is company A, right? We're just designing our first block, right? This is company B, correct? How do I solve for company 1? Just solve for, well, h of 0 is there. It's easy, right? How do I solve for this? Set x equal to 0. All right? And now you got, remember all those eigenfunctions or how to get the eigenvalues? Is that easy? So if I were to give you, I don't know, I'm just going to create something crazy. Y of n minus a1, oh, sorry. a1 of y of n minus 1 minus a2 of y of n minus 2, correct, is equal to 0, right? And then there's a trick where you can do this. Y, let's call it y minus, let's see, how does it work? A1, what was it, lambda? I think it's lambda minus A2 lambda squared is equal to 0. Remember that auxiliary equations? And you got to solve for lambda. Actually, this right here is actually equal to 1, I think. Is that correct? Then solve for lambda. Lambda is equal to, what do you call it? How do I want to do this? That's A, that's B, that's C. How do I want to do it? No, that's the quadratic. Hold up. I'm trying to remember my quadratic equations. That's that, that's that. No, wait. Hold up. It's minus 1 and minus 2. And the reason why I say that is that when you start solving these equations, you're going to realize this is the higher power. So let me show you what I'm trying to do. In the end, it's going to look like this. Lambda squared minus a1 lambda minus a2. There we go. That's what it looks like. Okay, does that make sense? And then lambda is equal to, what's that quadratic song? It's b squared not negative. Wait, x is equal to minus, yeah.
So it's
Negative b plus minus square root, yeah, b squared minus 4ac. Yeah. So now you're going to have to solve for that, okay? And then that's where you have a general solution, okay? I'm going to show you this, page 2. Okay, page 2. Where you're going to have y, I don't know, poles, question mark, of n. It's going to equal to general solutions, which is C1 of, let's see, lambda 1 of n plus C2 lambda 2 of n. Is that easy? And I think it's this right here, right? Because we're doing discrete numbers, right? It's not e to the power of lambda, right? Because e to the power of lambda gives you time, right? You're going to get into the Laplace transforms. Is that good? So now, how do you solve for this? Well, I just told you guys, y of n is equal to 0, right? Is equal to 1, okay? Is equal to c of 1, lambda 1, 0 plus c2 lambda 2, 0, right? And then basically, if you wanted to solve for one of them, I don't know, c1.
Plus,
Oh, wait, what do you mean? Plus c2?
yes, because that equals lambda 1 and lambda 2 equals 1.
Lambda 1 and lambda 2 equal 1?
Yeah.
No, these are things you got to solve for.
Oh, okay.
Yeah, that's from this. That's from this. You have to solve for that.
Okay, I see.
Okay, that's for a second order equation, okay?
Yeah.
So this is probably, we're literally doing your exam right now for the next one, right? Don't sleep. So C1 is equal to, I don't know, this is going to be a hardcore number. It might be half, I don't know, 1/2, question. It's going to be a nice number, okay? Is equal to, actually no, lambda, anything to the power of 0 is 1. There we go. That's what you meant. Sorry.
Yeah, that's what I meant.
Okay, sorry, I wasn't thinking. C1 is equal to minus C2. There we go. And then, ooh, that's a very key property. This is probably one of the biggest foundations in the world for good sinusoids. You'll see some good sinusoids with this kind of equation. And that's it. You're pretty much done. And that, funny enough, if you know that this and this are opposites, yeah, that's not that bad. So that means y of poles is equal to, well, whatever C, it's probably going to bother someone. C1 lambda 1 minus lambda 2 u of n. Don't forget this. This right here is plus 5 points, okay? Or I don't know. That's a lot of points. You forget that? He'll be picky. Have you noticed he's very picky on their exams? Yeah, that's 5 points right there. Don't forget it. Oh yeah, don't forget this here. That's 1 point. That's 1. Plus 1. Does that make sense? But what does this mean? What does y poles even mean? Let's go back. What did we do? We kicked the box, right? So we're getting the impulse response, right? Eventually, if I kick this box right here, it's going to settle, right? It's going to settle eventually to some number, I don't know. So if I put, well, this is my signal right there. Actually, that's it. If I run this through time, you're going to see it just wiggle around and just decay. Is that good? And what does this tell you about lambda 1 and lambda 2? What if lambda 1 was 1/2? What's 1/2 to the first power? Half, right? What's 1/2 to the second power? 1/4? So what happens? What's 1/2 to the infinity?
Infinity.
Or
0.
Kinda, yeah. You're gonna go all the way down to a small. It's gonna settle. Same thing with this right here, right? So what happens if this lambda 1 is something greater than 1, or let's just say it's 2? What's 2 to the power of infinity? Infinity. What does that mean? It's gonna blow up. So is that gonna help you with your guys' exams and your actual assignments? So if you see something wrong with these, all right, that means you did something wrong. So basically, what I'm trying to tell you is this right here, you're doing your impulse response of the feedback poles, okay? So this actually here is H poles. Cool? Now we got to do one final step. This is the hardest part. And this is where you actually have to do mathematics. I have to actually do work here? Yes, you do. You paid for this. H zeros, H poles, right? What's the total response? Well, I don't know, just do this, right? Kick the box right here, right? And we already kicked the box for this one and this one, right? What's the property that did you guys remember from chapter 1? If they're all in like or series, right? It's just simple convolution, correct?
Additivity.
Yeah, it's just all additivity. So y, well, kind of, yeah. Y of n, right? So if I want y of n, right? It's just going to be h zeros of n convolved with h of poles. All right? Is that good with everybody? Convolved with x of n. And why did I put that x of n there? What is this? That's what you're solving for, baby. Easy. So you already have this. That's the easy part. You got this. That's the hard part. Now convolve them together using mathematics. You're going to have to convolve. I don't know. I'm just going to throw some random number. Let's see. What did we have? What was it? I'm just going to create something. H of zeros is equal to, what do you call it? B0 D of this plus B of 1 D of n minus 1. Right? Easy. And then H poles is going to equal, I don't know, I'm just creating a number. C1 lambda 1 minus n minus lambda 2 of n, right? Is that good? And then don't forget the U of n. All right? Convolve them. What's H of n? H of n is equal to, and we got to do all this funny stuff, right? Where you got to, let's see, from infinity to minus infinity. Which one you want to do? I don't know. Zeros first. Do this. B of 0, actually, what's the definition? So I don't forget. It's, what do you call it? H of z, right? Of n regular, right? And then multiplied. H of p of, wait. K, it's like k minus n, right?
And the h of z is supposed to be h of k.
Oh, yeah, there's a k in there. And then that's right there. That's the thing we're shifting?
Yeah, that's the thing.
All right, perfect. Thank you. Anyways, d of k, correct? Plus b of 1, d of k minus 1, right? That's that first part. And then I'm going to do the second part. And then the second part is going to be, well, we got to replace all the n's with k minus n, correct? C of 1, right? Lambda 1 of k minus n, right? Hold up. Minus lambda 2 k minus n. Is that good with everybody? And then you just do your Kronecker deltas, this delta function times this right here, sift it out. Is that good? Is this a good kickstart for you guys' assignment? And let's see, what's the next part? Actually, hold up. Let me see what else. Let me see. ZSR. Yeah, literally the impulse response, what do you call it? Determines zero state response. ZSR. Oh, I see something else. Zero state response. Let me tell you another thing. So we just kicked this box, correct? all right? There was nothing that we did in the middle here. We didn't put any memory, correct? Is that understood with everybody? So if you were to solve for this actual like h of n, right, or h of n, right, you're going to get, this is actually right here, is actually our zero state response. Is that good with everybody? Now, how do you get the actual, like, what do you call it, zero input response? Now, this is the toughie. Okay. So let's build my companies. CA, California. CB, I don't know. What does CB stand for? H of zeros, H of poles, correct? How do I do a zero input response? Let's ground the input, right? What does that mean for, okay, hold up. Let's take this slow. I'm gonna draw my fingers. B a zero. You guys like direct transpose direct form too? It's just drawing the fingers. It literally looks like this. It's the easiest one to draw. That's why I pick it. D. All right. When I ground that, what does that mean? Zero, right? What's the output? Zero, right? So that means this doesn't even exist. Hooray, you're done. Does that make sense? So in reality, your biggest problem you're going to have to be solving for is this, okay? So now this is where the fun part starts happening. Plus, boom, boom, A1. Tell me if I'm wrong with the negatives, okay? Because I think you guys had some fun with those negatives, right? Yeah, they get pretty fun. D for David? No, D for dummy. Anyways. So you guys remember there's a ground right here, right? What does that mean about y at n is equal to 0? 0, correct? However, we have water in here, right? There's some type of water in here, so I'm just going to put water in there or something like that, correct? So now at y is equal to n equal, or before that, right? Before time, right? Yeah, I think that's what it is. So at this current state, correct? There's nothing. It's empty, right? It's grounded. But we have some memory in here, right? I'm just going to put, I don't know, minus 2 volts or whatever. Does that go with everybody? So I'm just putting memory in there, all right? So what's that? Y is equal to n minus 1. 1, right? So I'm just choosing this, okay? The company says there is some residue, whatever. Y is equal to n minus 2. Minus 2 or something like that. So what are you going to do? Solve those auxiliary equations again. So lambda squared minus a1 lambda minus a2 is equal to 0, right? You're going to have to do all this all over again to where you get your lambda is equal to, God, negative b plus or minus the square root of b squared minus 4 ac all over 2a. Man, easy stuff, right? Then you're going to have a y, what do you call it?
Y equals,
How do I want to call this one? I'm going to call this one, I'll just give you the answer, ZIR.
0.
N is equal to, there we go. And you're going to get something like this, C1 of lambda 1n plus C2 lambda 2. Does that make sense with everybody? However, you're already given the first point, which is, what do you call it? N is equal to 0 is equal to 0, right? But you can't really do much other than C1 is equal to minus C2. Guess that's how it was. No, something else has to happen. You might get another variable in here. I'm not so sure. I don't like this. Something else needs to happen here. because it can't be 0. It has to be something other than that, because you need to do this. N is equal to minus 1 is equal to the 1, and then you got to do something crazy with this. But it's not going to be as difficult as you think, okay? And then guess what? Let me show you. Next page, 5. Page 6. So let's just go over what I'm trying to show you. H zeros, H poles, correct? So when I grounded this, right, nothing really happens, correct? But then when well, this is also grounded, right? But something does spit out of this, right? What does that mean about H zeros? It doesn't matter. We're not relying on it at all. It's doing nothing. Okay? So in reality, the output coming from here is going to be your Y0 input response. Your system relating, or your system's response to no input, but there is memory. Okay? Now I'm going to show you something harder. You guys like harder? Oh man, I don't like hard. I want to go home. I want to go to Halloween. Or Nevada Day. Or I don't know, whatever you guys like to celebrate. I don't know. So I'm going to charge this. Wait, there's no capacitors in there. I'll put a capacitor in here. Plus minus 5 volts or whatever, right? There's technically nothing. So what happens when I have an input, right? And some memory, right? I have something in that system, plus there's an input. All right? So let me show you one last thing before I gotta leave. If I have, what do you call it? The ZIR, right? That's what we just solved for right here, right? And then if I do following, ZSR, right? Combine this with an adder. Can we agree that instead of doing this fat problem right here, which is this big scary problem, I don't know, right? Very scary problem, right? We can dissect it into this. 2 separate different problems. All you got to do is just add them at the end. Does that make sense with everybody? Total response. That's how you do your assignment. So you're basically doing 2 things to get 1 problem, all right? If I were to give you this problem, this looks pretty scary, right? But if you just tackle it from this angle and this angle, you're pretty much good to go. So that's what I have you for the assignment. I'll upload this later on. You're solving for the ZSR, correct? I give you a kick, right? And then anything before time, bless you, is 0, correct? Is that good? And then, oh, that's where my problem 2 was. There you go. I'll edit this one. I don't like this one. There you go. And then determine the values of R using the Schwarz inequality. Okay, this should help you with this, to know if it's going to blow up or not. Using your program, calculate the ZIR. So you already have your charges in there. Does that go with everybody? Then using your program, calculate the impulse response. So you're putting literally an impulse. So what's the input right here? X is equal to 0 is 1 of length, whatever. Right? Easy? But you're going to be changing this. That's the hard part. Okay? You already did this in the last assignment. Okay? And what about here? What's your input? Exactly what you've just been doing in computer assignment 3. But you're just, what do you call it? Systems. Okay. You're doing something different. You're doing what you did in assignment 3, but you're also adding memory to it. Okay? And then you're adding what you did from 3 and 4. So this right here, you're adding this. You're adding the impulse response, right? The ZSR plus the ZIR equals the total response, right? So what's the answer for 3? It's just the ZSR, right? Actually, better yet, what's the answer to 5? It's going to be 3 plus 4. Or actually, what's the answer to 6? Is going to be the answer to, 3. Oh, my computer's lagging. 3 plus 4. So how to get problem 6 done? 3 plus 4. Is that good? Oh, why is my computer laggy? So anyways, this is the hard part. It's not hard. You're just brute forcing the answer. But this right here proves to you that you can do it 2 different ways and add those 2 answers. You're literally doing the following. So this is that problem. This is problem 5, right? Prob 5. 5, correct? And this is problem 4. And this is problem 3. Okay, and then this right here is problem 6. Any questions about your computer assignment? When's your next exam due?
You moved it until November 3rd.
November 3rd?
Yes.
So you guys are going to have a happy holiday and study all weekend? So this shouldn't be that bad of an assignment, okay? So I'll get with you, Joanna, to see how we're going to do and make an announcement. So if it's due, the exam's on the 3rd, due midnight that day too? Is that good? All right.
Or 2 days after.
Nah, we're going to make it due there so we can start Laplace transforms.
Okay.
All right? Because that's the big cheese of this class. It's the big meat and cheese. It's the biggest thing ever. And you'll see why. Darn, I don't like... Instead of doing trigonometry, you're going to do calculus. Instead of doing difference equations, convolutions, we're going to go right into math, like multiplication and Laplace. It's going to be a lot of fun. All right? Have a good day, everybody.
Thank you.